Hi, my name is Mike Rayleigh. I'm PAC International's Director of Engineering. Thanks everybody for joining us. We really appreciate everybody being here. Today's webinar is Design Details for Good Acoustics. This is part 1 on walls. We have a part 2 on ceilings, which I do believe we will be doing next month. We'll provide a recording of this. If you've got questions about CEU credits and all that kind of stuff, you can put those in the Q&A. This is registered with AIA, and I think that anybody that registered for this, if you gave us an AIA number, we'll handle all the reporting of that for you. If you need sort of a certificate of completion for something else, some other organization or whatever, we're happy to kind of just give you a certificate so that you could see that. Taylor just put her email in probably the chat, so you can go grab her email, send something to her. She's the one that takes care of all of that for us. And with that being said, we'll go ahead and get into it. So the point of this presentation is, design details. It's in the title, and we're going to talk specifically about walls. And a lot of times when we're specifying, acoustical performance, acoustical products, these kinds of things, we're looking at acoustical lab test reports, right? For an assembly, for a wall, we're looking at an STC rating for a wall, see if we meet a code minimum or a project requirement, whatever that may be. But the way we test those walls in a lab is sort of an idealized condition. So here's a picture of a wall test in a lab. And you can see that it's nice and clean. They haven't, finished sealing it in or anything like that. But you could see the level of detail that they put into the construction. There's lines marked for every screw. All of the screws are in nice alignment, and there's a lot of details. Also, there's no penetrations in the wall. There's no electrical boxes or anything like that. There's nothing mounted on the wall, right? We're testing just the wall design itself, and that's important information, but it doesn't really represent the real world. In the real world, we have all this other stuff that we have to deal with. We have cabinets that are mounted on the walls. We have electrical outlets and lights, junction boxes, these kinds of things that go on the walls. We have TVs or cabinets, all of this stuff that gets mounted in and on the walls. And those things affect the acoustical performance of the wall in the real world, which is ultimately what we care about, because we want to make sure that we're, adequately isolating sound from one space to the other. So how do we address all of these issues? Because they don't show up in an acoustical test report. So first, before we get into the specifics of details and some detailed drawings and acoustical test data for those things, I want to first sort of lay a conceptual framework for how we think about this. So when we're looking at sound transmission through a wall, from our whole bunch of speakers over here on the left to somebody trying to focus and read in a quiet environment, whatever it may be over on the right. So we have our sound source, and then I like to think about this in terms of two primary types of sound transmission paths. So in blue, we have the structure path, and in green, we have the cavity path. So the structure path would be, let's see if I can do a little laser pointer. So the structure path is here. We have the sound waves, which are just air pressure fluctuations that push on the drywall, for instance, on this wall, make it vibrate. That's attached to the stud, so it makes the stud vibrate. And then, maybe we have some resilient element that isolates these two, or maybe not. Maybe it's directly attached. So the stud moves, and then that makes the drywall on the other side move, which makes the air on this side move, and then that's what we hear. The cavity path, air, sound hits this drywall, makes the drywall vibrate back and forth, makes the air in the cavity vibrate back and forth, and then that gets transmitted through. This makes this drywall vibrate and go through. So we have these two types of transmission paths. We have the structure path, the cavity path, and the sum of those paths, or all of those different kinds of paths that fit within those two categories, winds up being the total transmitted sound. So we have to think about our isolation for both the structural path and the cavity path. And so sometimes we might have something like a junction box, the little blue rectangle there at the bottom, that affects our cavity path because we've put a hole in the drywall, and so that's going to let more sound through. So we have our sound source, we have our structure path and our cavity path, our incident sound, that's the same. Same amount of sound goes through the structure path, but now we have more sound through the cavity path, and our total transmitted sound is higher because we have more sound coming through that cavity path. Alternatively, we could have something where we've affected our structural path. So in this case, we've got a cabinet that's mounted to the wall. And in order to mount the cabinet, we have a rigid backing, 1/2 inch OSB or plywood, something like that. And so now we've got this rigid connection all the way through for our structural path. So we have more sound that's transmitted through our structural path. Maybe our cavity path is actually a little bit lower because we've got the extra weight mass of the plywood backing. But our total transmitted sound is higher now because we have more sound coming through the structural path. And maybe a helpful analogy for this, especially for those of you architects that maybe do a lot of work in sustainable building, high performance buildings, especially for thermal envelope, air barriers, those kinds of things. You can think of that structural path as sort of analogous to thermal bridging. So if you've got your building envelope and you're looking for improving the thermal insulation of that building envelope, it's not as simple as just specifying a higher R value insulation to say go in your stud cavities, because you have this other transmission path for heat that would be through those connections from the outside of your building envelope to the inside of your building envelope. And usually that's a stud, and that'll transmit more heat. So you can get this sort of cumulative composite insulation value for your assembly. And if you can decouple those thermal bridges, and there's a whole bunch of different ways that you can do that. And that's not my area of expertise, but there's a bunch of different ways that you can do that, and that will, without changing the actual thermal insulation that's in your cavity, that can improve the overall insulation value of your wall because you've decoupled those structural connections. It's the same sort of thing for acoustics, very analogous. And sometimes what might work for acoustics might also work for thermal insulation. When we're talking about the cavity path in acoustics, we really want, I think the way to think about it is you want a continuous mass layer. And that could be, it's often drywall for walls. Could be CMU block or concrete or mass timber, but you want this continuous mass layer. And so anytime you have an interruption in that, you need to figure out how to seal it some way. And ideally, you want that seal to at least be somewhat close to the mass of this other continuous mass layer. And so you can think about that like a continuous air barrier. So here in this, we have this pink line and this detail that denotes the whole, that denotes your air barrier. And the idea here is that you can take your pencil and you can trace this air barrier and not have to ever lift your pencil. And so the tricky bit is not here just kind of the standard homogeneous part of your building facade. You can just specify the right product material there and you can get your air barrier. But it's all these details where you might have a gap. You might have to lift your pencil. And so you have to figure out how to make that line continuous. So in acoustics, it's the same kind of thing, right? We have to make sure that we have this continuous mass layer. And so if you take these two ideas, really for the structural one, you can kind of trace the path through a detail or a wall, an assembly detail or a junction detail, something like that. And for the structural path, if you can trace it through your pencil and you have all rigid connections that go from one side to the other, that may be an issue acoustically. That may be something that will transmit sound that could be an issue. And then for the cavity path, you want to trace your mass barrier. And if you have any gaps in that one, that may be an issue acoustically too. So we'll think about these two approaches as we go through all these sort of specific details in this presentation. And to really hammer home the importance of paying attention to all of these details, I have an example here. And I talk about trying to build a soundproof space. And I hate that term because nothing's really soundproof. It just lets in less sound or lets out less sound. But if you're trying to build this space that contains sound, it's like trying to build a submarine, right? You don't want to let any water in from any direction in a submarine, and even a tiny little leak will sink the thing. And acoustically, even a tiny little leak can sink you from an acoustical standpoint. So here's a double stud wall. For some scale, it's 8 foot tall, 12 foot wide. And in this case, the wall I picked was STC 62. And I went and did this with actual test data. I think I grabbed this from the National Research Council of Canada data. If you put a 1 square inch hole in that wall, 1 inch by 1 inch, it goes down to an STC 41. Just a tiny little hole. And that hole is 0.007% of the total area of that wall. And so you can think this could be just a hole for an outlet. This could be the crack underneath a door. All of these little things. It doesn't need to be much in order to dramatically reduce the acoustical performance of your assembly. So all of these details are critical in order to actually achieve in the real world the acoustical performance that we're sort of expecting based off of laboratory test results. So now we're going to go through some specific details, and I've kind of categorized them based off of the cavity path, structural path, or a combination of both of those as really the primary things that we're looking for in each of these. And we'll talk about how, really all of these, you could say that there's some element of the cavity path and the structural path. You always need to be paying attention to both of those. But I've categorized these based on the predominant thing that's the problem we start trying to solve. So first, we'll start out with cavity paths and electrical boxes. So this is the one, we have electrical boxes in all kinds of walls. And there's a whole host of different ways that we can do this. And here's test data for a bunch of these. This is from the National Research Council of Canada. They've done a bunch of testing, acoustical testing over the years on things like this that are just basic bits of building and how we build things and what effect that has on acoustical performance. So they're a great resource, and a lot of us acousticians turn to them and their reports that they've done over past many decades for information just like this. So this is all real test data where they change sort of just one variable at a time. So these are really good comparisons. So we have a base wall, it's 2x4 wood studs, RC, a few layers of drywall. It's SDC 55, this test configuration. And then you can see if you have back-to-back electrical boxes, right? You have this weak point in your wall, and this is just one electrical box on either side of this wall. And it reduces your SDC rating by 5 points. And so if you're thinking about building code for like multifamily residential construction, you go from something that's comfortably above the code minimum of SDC 50 to something that barely meets that code minimum. And that's with one pair of back-to-back electrical boxes. But you can think about a kitchen where you might have many of these, or if you're thinking about offices or hospitals or something like that, right? In a hospital, you have back-to-back head walls and you have a whole bunch of penetrations in those walls. The situation is going to be worse than this. So one way that you can try to address this is you separate these things further from each other so that the sound has to travel further through them, right? You're not really addressing the structural path per se, or really the cavity path. You haven't actually changed anything. You just make the sound have to travel further through that cavity path to get from one weak point to the other. And that can improve your SDC rating and get it back to basically where we started. But this is really hard to actually detail in the field and make sure that you're always maintaining that. And I was talking to PAC's other acoustician, Drake, and he was saying, yeah, when I was a consultant, I used to always try and do this, but we were never able to actually achieve it on a job site. It's just really hard to specify in detail and control. So really the solution here is add a mass loaded material. Usually it's a putty pad. There's fire rated putty pads, and if it's a fire rated wall, you might have to do it anyways for fire. But that adds that mass. And so you can see here, we have now this sort of continuous mass layer that goes around, right? So now we can take our pencil, we can trace that mass layer all the way across the wall. And that brings us back to our original SDC rating. When you have isolation, maybe it's resilient channel, maybe it's clips and hat channel or something like that, that holds the drywall out from the wall, there's often a question of, okay, how do I make the connection between the electrical box that's sitting up against the stud and have it go all the way out through the drywall like it normally would if we have this offset? So that's a really simple thing. There's mud rings or extension rings for electrical boxes, and they come in different depths. And so you just add that onto the face of your electrical box. Make sure you have your putty pad that goes all the way around that, seals all of the gaps for both of them and the junction between the two of them. And then you want to make sure that you have, so this is one of those where you could, maybe we're talking about cavity paths here, but you could create a structural path issue. So you've got this drywall that's rigidly attached to the stud here. This box is rigidly attached to the stud. And then if this is rigidly attached to the drywall, then you can transmit some energy through there. Now, it's one box. It's not that big of a surface area. It may not be the end of the world. But if you're going for very high levels of sound isolation, this may become the weakest link, and it may matter and limit the total acoustical performance of your wall. So you want to make sure that there's a little gap between the drywall and this box, but then you seal that with acoustical sealant or fire-rated acoustical sealant if it's a fire-rated wall, of course. Okay, so another instance in a wall where we create a break in our mass layer, our continuous mass barrier, is control joints, right? If we have a long expanse of a drywall wall, we have to put a control joint there to allow for expansion of contraction of the drywall relative to the framing and all of these bits. But that control joint is just a gap. So we need to seal that control joint. And this is another one of those, oftentimes acoustics and fire can be at odds with each other. Sometimes what works well for fire does not work well for acoustics. And we've got another presentation on that, which I think we'll do in a couple months. We'll do or maybe 3 months from now, we'll do our acoustics and fire presentation. Control joints is a situation where acoustics and fire, the solution is kind of similar for both of them. So we have a gap here that we've opened up between our layers of drywall that we need to seal. We need to seal it for sound. If it's a fire-rated wall, we also need to seal it for fire. So we put some, fire-rated and acoustical sealant. And acoustical sealant is non-hardening, so it maintains its resiliency, so it doesn't create a sort of a rigid bridge between things that could transmit sound. But also it means as this gap moves, it will maintain its resiliency, so it'll stretch and squish with that, small changes in this gap, so that it always maintains that tight seal. It doesn't open up gaps over time as it, dries and shrinks or something like that. So here we have our drywall, we have our seal, and then we have these drywall backers that are attached to an additional stud in here. And now you'll notice, so this is a thing, so our goal here is to solve a cavity path issue. We've put the sealant in here to seal up this hole. But we also put this drywall to provide some more mass back here, and this is for acoustics and fire. Here's some GA file numbers for these control joints that show this. If we make this drywall in here attached to the stud, touch the drywall on both sides, then now we've created this continuous structural path. So we've solved the cavity path issue, but now we've created a structural path issue. So you can see there's a very small gap here and here and here, so that there's not a continuous path. Now here we have a continuous path, drywall, stud, drywall, but we have a gap. So we have a break, we have to lift our pencil, we're good for the structural path. Here's a 1 hour version of this. I think 1 hour you could have a single layer of drywall on each side. I've put 2 in here because we've actually tested it this way. So we've got acoustical test data that shows that this works, sort of maintains the acoustical integrity of this wall. And then 2 hours, you would just have 2 layers of drywall on either side. We don't have an acoustical test for this, but it would be at least as good as this SDC64 probably. Okay, so there's a couple cavity path options. Now we're going to go on and talk about some different structural path scenarios. So first one, this is a big one, is cabinets and other heavy static loads that get mounted to a wall, and specifically a wall where you have isolation. So it could be cabinets, could be headboards or floating nightstands in a hotel, for example. So let's take very basic wall. I was an acoustical consultant. I did a lot of multifamily apartment projects here in the Portland, Oregon area. And most of those, the demising walls, were 2x4 wood studs with resilient channel and some number of layers of drywall on either side. So here we have a tested wall that in this configuration, this test got STC54. If you mount a cabinet on it, which is typical, the way I typically saw this done when I was a consultant, is the contractor will put 1/2-inch OSB or plywood backing between the studs and the drywall. Because if you just attach the cabinet to the drywall, through the drywall and into the studs, when you've got this resilient channel there, when they tighten the cabinet in, it'll start crushing that drywall and it'll create issues, cracks, all these kinds of things, right? It'll hamper your installation. So they put this spacer essentially back here, and it also just gives you a wider target. But when you do that, you create this structural path issue, right? Now you have this rigid path. We can go trace all these rigid connections from one side to the other. It's an STC46. So you've taken a wall that was comfortably above your, International Building Code minimum of STC50, and you've made it well below it. So now you have a wall that no longer meets the code minimum. So what you need to do is you need to break that path. You need some kind of isolation. So again, we trace the structural path. Oh, we have a break here. We have to lift our pencil. So you can use an acoustically isolated backer. You need some sort of resilient element that won't transmit as much of that vibration energy from one side to the other. You also need to make sure that whatever that thing is obviously strong enough to hold the cabinet, and a cabinet not just empty, but full of dishes and all of these kinds of things. But when you do that, if you break that transmission path, you can bring the wall back to its, roughly back to its original level of performance, close enough, right? In this case, you get the same SDC rating. A similar situation occurs if you're using clips and hat channel, right? That's another common isolation approach for walls. And typically with clips, you will use a 25 gauge or an 18 mil hat channel. And 18 mil steel is very thin. You don't really want to try and hang cabinets or other heavy items off of that. So you need some other heavier duty backer that you can attach the cabinets to. So there again are acoustically isolated backers that are designed to work with clip and hat channel systems that maintain your acoustic isolation but give you a stronger, stiffer, more rigid and bigger target to hit to mount cabinets or other things too. Very similar is grab bars and handrails. The difference with these really is just that they're not as much of a static load, but it's a dynamic load, right? So if somebody's pushing on it or they happen to fall and they need to grab and catch it, again, we need to mount these. The typical way of mounting grab bars, handrails is back to structure, but that would create a rigid transmission path for your sound. And so again, we need an acoustically isolated backer. And here we need to make sure that the backer can meet the requirements for the loading for grab bars and handrails. And I think for handrails, it's 200 pounds in any direction, and grab bars, I believe, is 250 pounds. So you want to make sure that you can maintain, hold that load, but still maintain this acoustic isolation, at least when the load's not applied to it. And so for all of these, whenever you're looking at these details, if you can get acoustical test data for these, and you can get sort of an A/B comparison of a with and without, whatever the acoustical product is, or whatever the detail is of mounting a cabinet to a wall, and you can get back-to-back tests in the same lab, same construction, and all of these kinds of things. That's the most informative way of looking at this, to see what effect these things have. And that's, again, why a lot of us acousticians go to NRC, the National Research Council of Canada, because they will go through these big, extensive test series where you can see those comparisons. But also if you're looking for, a manufacturer's test data for a product, see if they have this A/B comparison, like seals for gaps or something. They test it without the seal, and then they test it with the seal. All right, another example here of a structural path that we need to look at is deflection heads. And I realize there's probably not a deflection head in here, but I wanted a picture that had a bunch of steel studs in it, and this is what I could get that was free pictures I could use. So here's a deflection head detail. So when we have this, we need to decouple the wall from the structure up above. So in this case, say we've got impact on this wall, and say maybe this is this building is not completely stacked. The floor plans aren't completely stacked. Say maybe it's an office building or something, and or just condos, but this is, it's a penthouse up above, so it spans over 2 units down below or something like that. So somebody could be walking right here. And if you had this steel stud rigidly connected to your concrete, that impact energy goes into this concrete and then comes down your steel stud and can get radiated out, especially this drywall that's directly attached to it. And that can be a significant flanking path that can limit the sound isolation between these spaces. So we want to decouple this connection here. So we have an isolator, acoustical isolator here. Usually it's a rubber kind of grommet and things like that. And then fiberglass or mineral wool. Mineral wool is usually used if it's a fire-rated head of wall. Sometimes fiberglass can be in there. It depends on the UL design that you're looking at. In this case, we also have the added element of, so this is not just a decoupling here of this, but we have a deflection head where we need to allow these two things to move independently of each other. And so we have this drywall here that slides over this drywall. Now, if we just left this gap up here, we've addressed the structural path, but now we've created a cavity path issue. Right, so we always have to be thinking about both of these things when we're going for these acoustical solutions, because we could wind up solving one issue and creating another issue. So we have these two that slip next to each other, and you can see here there's a screw that attaches this to the hat channel, but this slides, right? And you could do this, this would be clips and hat channel. This could be drywall directly attached if you don't need the isolation here, or it could be resilient channel as well. And this particular fire track here has this offset that bumps out, so it holds this drywall out to account for the extra distance of clips and hat channel. I think there's also versions for resilient channel and different layers of drywall and these kinds of things. So all of these different details. So there's a lot of different moving pieces and details and things like that to pay attention to here, both for acoustics but also for fire, for, constructability, your deflection. So a lot of different details to pay attention to. And if you just think about those, cavity path, structural path, tracing those things with your pencil or your mouse, it'll help out with a lot of these details. All right, furred walls. So say you've got a CMU block wall, an existing wall. This comes up a lot in sort of strip mall situations where you've got two different tenants next to each other. We have a lot of these where it's a fitness space. Maybe they're going to have a spin class, or they're going to have a sound system that's going to be really loud. And next to it is a daycare or an attorney's office or a therapist's office or a doctor's office or something like that. And obviously you want good sound isolation between those two spaces. And you have an existing wall that's already there. That's part of the existing base building. It's fire rated. You don't really want to touch that. So you need to add something to it. And what you want to add to it, maybe you've got a fairly tall wall, and if you design studs that could just do the whole clear vertical span, you'd need heavier gauge studs or thicker studs that are going to take up more space. So if you can tie back to the existing structural wall, you can reduce the size of your studs or the gauge of your studs or whatever it may be, and maybe save some cost and save some space. So you want to tie it back. But you need acoustic isolation. You don't want to create this rigid connection from this existing wall to your new wall, because then you won't get all the acoustical benefit of this other wall. So we have these isolated tiebacks. So it's just an L bracket and then with a rubber isolator. So again, you break this structural path. And again, you want to make sure that you take care of your cavity path. Two, you want to make sure that this is all sealed up and things, and having this kind of double wall situation can be helpful, because if there's penetrations in this wall, now if it's a fire rated wall, hopefully there's not a bunch of penetrations in it. But if there are, and maybe you can't seal them, you can't get to the back side, the other side of this is another tenant, you can't control this space, you can't seal everything up over here, you just don't know what's going on over there, you can use your side plus this new wall to make sure you've sealed up and addressed the cavity path too. Shear walls. So again, I've worked as an acoustical consultant in Oregon for most of my career, and in Oregon, we're in a seismic zone, and so we run into shear walls a ton here. And the trickiest thing with shear walls is when you have a double shear wall. So you have your shear panels on both sides of the wall. And what this means is that we don't have this clear cavity path. So if you came in here and you put drywall just directly over this, right? Sorry, we don't have this clear separated structural path. So your sound hits this side, rigid connection from the drywall to your shear panel, rigid connection from the shear panel to the stud to shear panel to drywall, and the sound just comes right through here. So if you add another layer of drywall on this side, this rating only goes up a few more points, and you don't get anywhere near the code minimum. So what we want to do is we want to break that structural path. So one of the ways that we could try to do that is with a resilient channel, but that creates this very small air cavity here. And so while we have essentially decoupled that structural path, right, the shear panel can move somewhat independently of the drywall. That's very small airspace. The air in there moves as a spring. That air has some stiffness, right? And that's how sound is transmitted. I mean, that we hear. It's through air. And so if the shear panel moves, that air in between moves, and it moves the drywall still. So we need to really expand that gap between the two. So one way we can do that is, an extra wall, but that takes up a lot of space. So, clips and hat channel is another solution here. Any way that you could get that a larger airspace, but also maintain that break in the structural path. And as you come here, you want to make sure that you don't tie anything back to this that's going to create this rigid structural path. If you only have shear panels on one side, if you can put the shear panel on the side opposite, your resilient channel, clips, whatever your acoustic isolation is, then that can work really well and you don't have to worry about this as much and you'll get better performance out of your wall. But sometimes that's hard to do, even if you have only a single shear panel. If you think about a kitchen that's on a corridor wall, so it's kitchen wall and then the corridor, putting your sound isolation on the kitchen side creates an issue with hanging cabinets and all this kind of stuff. Now you could use acoustically isolated backers like we talked about, but that adds more detailing and specifications and things that you've got to pay attention to. So it complicates the design and construction of that kitchen. So you say, okay, well, let's put the isolation on the corridor side. Well, but if you put and then put the shear panel on the kitchen side. Well, but if you put the shear panel on that kitchen side, that goes up when the building's framed. And then your contractors, your subs for electrical and plumbing have to come through and run all of that in the wall and then go through that shear panel to get to your kitchen. That adds complication and some cost to it. So often you wind up wanting to put the shear panel on the corridor side too. So then you wind up with shear panel and acoustic isolation on the same side, even though you only have a single shear panel. So that can become an issue. So you got to look at those kinds of details. All right, I think we're doing all right on time. Cool. So now we're going to talk about the last category, which is combination of cavity and structural path. So again, in all of these, you always have to pay attention to both of these sort of big categories, cavity and structural path. But the other ones that we've talked about, one of the two was sort of the primary problem that we were trying to solve. And these, really, we're trying to solve both of these at the same time. So the first thing we're going to talk about is door and window jambs. So detailing around these can be really tricky when you have sound isolation. So I guess the first thing to talk about here is if your door or your window is by far the weakest link in your wall, you might not really need much sound isolation on your wall. So think about that too. Like, let's make sure that if we're going to put a lot of time and effort and money into acoustical solutions, we're doing it in a way that makes sense. So if you've got a corridor door like in a hospital that's got a big undercut underneath it that you're not going to put a seal on, all that sound's going to go right through that. That's more than that 1-inch gap that we had in our STC 62 wall that took it down to an STC 41. So throwing a bunch of money at the wall is not really going to make it any better. Your submarine's still going to sink. But if you've got an apartment building that overlooks the highway, and you know that highway noise is going to be an issue in the apartments, and so you've gone to the effort and the expense of specifying, selecting higher performing windows and maybe shrinking the size of those windows down as much as possible while you still let in a lot of light and have all the benefits of the natural light. You've done things to sort of minimize the acoustical weak link of the windows. Well, then it very well may make sense to improve the acoustical performance of your wall, put sound isolation in that wall. And then you need to figure out the detail between your sound isolation in the wall and that door or window. This also comes up in office spaces, recording studios, things like that, where maybe we have an STC rated door. And so we have a higher performing door. So we need to make sure that at least for our wall, we're not creating structural connections across this and that we're sealing this all up. Now we obviously have the door or window, head and jamb that could be a structural path through here, but we're just going to kind of ignore that and hope that the door or window was tested with the door frame and that frame is designed such that it provides decent sound isolation across it. So we want to make sure that when we have our isolation on this side, we keep our drywall floating. And when we come back and we have this return over here, it doesn't create a rigid connection to this, because at least this is sort of if this is transmitting, your door frame is transmitting some sound, at least it's a fairly small area. So it's not transmitting as much total sound energy. But if we then connect it to the drywall, that's a much bigger, we've got a much bigger speaker that's going to transmit more sound. So we keep that separate, but we want to seal it so we don't get any gaps. And then we want to have this return to seal this gap over here. So again, we want to continue this continuous mass layer all the way across. And this is it at a head, right? We can see our header here, and then this is at a jam too. We do the same kind of thing where it comes and turns. A window is very similar for the head and jam. We might have a bigger return here, but where a window gets trickier is at the sill, because the head and jam, we have this kind of floating drywall. We have some L angle here that's tied to our isolator and our hat channel here so that we can support this, provide some rigidity for this corner so it's not going to crack and things like that. But these aren't going to see a whole lot of pressure, weight, load typically. A sill will. You might put some plants in your windowsill. My kids might climb on it, these kinds of things, right? Your dog might put its paws up there to look out the window and bark at the squirrels, whatever it may be. And so you don't want this to crack or have any issues there. So this is one of those things where we're going to make an acoustical compromise. And so this probably, your sill needs to be rigidly attached to this. But we want to still minimize that area that's rigidly attached. So this bit down here, we're going to float up here, and we're going to put some blocking back here. We're not going to attach it to it, but this is going to minimize the potential movement of this. So if somebody comes and leans up against this or something, it doesn't get pushed back. And this is also to support this so we don't have this cantilever. Like, we could move our isolation up here, but then this would be cantilevered out. And if somebody comes and sits on the edge, it's going to crack, right? Same thing if we have a wood sill. Apparently, I missed a label here. That should not be drywall corner bead. All right, now we'll talk about intersections. And intersections can get complicated both just for acoustics, but when we also throw in that a lot of times for these intersections, we have to pay attention to fire ratings as well. Then that can get really tricky. And this is one of those where acoustics and fire can often be at odds with each other. So over here on the left, we have a non-rated wall here that ties into a rated wall. So say this is an interior partition within an apartment, between a bedroom and a bathroom or two bedrooms, and then it ties into a demising wall, between the unit and the corridor or between two units. So we want to make sure that we don't have, we want to go trace, do we have a continuous mass layer here? So in this case, we've got this drywall that goes all the way across, and here we have the wood, we've got sealant here, and that's continuous all the way across. Obviously, this is continuous all the way across. Now, we don't care about sound isolation between these two that much, right? At least it's not a code requirement for isolation between bedrooms or bedroom and bathroom within the same unit. So this structural path, all this is okay. But we want to look at, are there rigid paths here? So this is fine. Here, actually, we can trace this. So this is tricky. So for fire, right, this is where fire creates some limitations. We can't necessarily have a gap here. Perhaps we could pull this blocking off and leave a gap here, but I don't know if that works for fire. So you'd have to pay attention to that detail. But this is also, we've got a long path. We're going to try and minimize our weak links. Right, so we have this long path, and it's got to go through this drywall, then this 2x4, then these 2x4s at the end of here. There's going to be some reduction in the sound through each one of these sort of junctions, and the idea is that there's enough here where it's probably not an issue. But it also depends on how much sound isolation you're trying to achieve between here. If you're going for a code minimum of SDC 50, this detail probably not an issue. If you're going for SDC 60 or 65, because super high-end condos or something like that, you may need to think more about this detail here. Here's what this looks like if it's a fire rated one into a fire rated one. And we can use this blocking. The key here for fire rating is that we can use the wood blocking to break the drywall layer, because wood studs work as blocking. And so you can break the drywall with those. When we get into steel, we can't use the steel studs as fire blocking. And so if we have this non-rated partition that intersects with a rated partition, this creates an issue. So we need to seal this. This is fine here. But the trick is, if you want to stop sound transmission both this way, right, from the corridor into units, but also between these two units, And you could run into this, this could be, these are apartments, right? And so you have a fire rated wall running into a fire rated wall. And you want to stop this continuous drywall across here, because here you have this continuous rigid path that goes from one side to the other, right? And so we want to intercept that. And here you can see that we don't have any rigid connections, right? There's a gap here, a gap here. This stud is held off from this, so there's no rigid connection here. There's a gap here, but it's sealed, but it's an acoustical sealant, so it's resilient. Maybe a fire rated sealant, again, if this is fire rated, should have said fire. But we have all these gaps, and we also have continuous mass layers. So again, you just get out your pencil, start tracing things through, and see, do we have any rigid paths that I can follow? And do we have a continuous mass layer all the way across that I can follow? Walls to ceilings, similar sort of situation, setup, same approach. Wood, again, is a little bit simpler because we can use the wood studs to intersect the ceiling here. And again, you got to think about, like, okay, so we've got this isolation between this. Maybe this is an amenity space up above that bridges across a unit, or this is just a unit and, things don't stack. This is a bedroom wall. So here we do have, this path. This is a rigid path here up. So that could be an issue. Now here we have maybe some sound isolation up at the top, a mat underneath the gypsum concrete. So we do have this acoustical break here. So that's helpful. And again, this is kind of a circuitous path. So we can do that if it's fire rated, things like that. We have isolation down here too. It's a similar sort of situation. I didn't put one in there I didn't put a similar one for steel, because steel is really tricky because you can't break this. We have another presentation that I mentioned that's on fire and acoustics, and I do have an example of a steel wall ceiling intersection in there, but those are tricky. And so those are ones to really, get out your details, talk to your fire protection engineer and your acoustical engineer, and work through those details. Wall to ceiling, this is steel. This would be like steel to concrete. So here again, we have this, this is without deflection track, but we have still the acoustic isolation here and our sealant. So similar kind of thing to the deflection head that I showed earlier. Wall to floor. Here again, we're kind of creating a bathtub for this. So this would be, kind of typical multifamily construction, lightweight wood framed construction. We've got, wood joists, wood trusses, and often we're going to have a gypsum concrete topping on an underlayment. So that's kind of our separation here. And then we have our drywall that comes in. We don't want to create a rigid connection between this and this. And we don't want to have a rigid connection between the gypsum concrete and here, because that could transmit sound across, or it could transmit sound up into this drywall, right? So everything here is kind of isolated, right? And again, we're just tracing all of these paths, paying attention to all of these details, and making sure that everything is sealed. We want to make sure that we've got a seal here. We've got a seal here, so we don't have any leaks where the sound can get into the wall. Same kind of thing, wall to floor at steel. And I've, as a consultant, there were a lot of projects. I remember one that was an office space, and there were two conference rooms right next to each other, and they were having issues. They could hear each other. They didn't have the level of sound separation and privacy between these two, conference spaces, and they were doing video conferences and things like that in there. And so I went and I put a speaker in one, and I played like pink noise, basically just sounds like TV static. I played it in one. I went in the other room and listened. I also did sound level measurements, document everything, but really just use my ears to listen. And one of the places where I heard sound coming from was at the bottom of the wall where the drywall met the floor. And in that case, there was a base molding that's just the vinyl molding that's pretty typical in offices that was there. And I got down and I took a business card, and I could just slide my business card all the way under. Right, so there was no seal there, and a bunch of sound was coming through that. So all of these little gaps, a 1 square inch hole in a 8-foot by 12-foot wall can, dramatically reduce the STC rating and the sound isolation of your wall. So you got to make sure that you seal all of these little bits and pieces up. And it's not all that complicated to do, but it is, nitpicky kind of painstaking work to go do it. Make sure you get it done right. All right, I think the last thing we have here, and then we'll have some time for questions. Last bit is window mullions. And window mullions are really tricky ones. they create a lot of issues. And part of that is because we have this cavity path. So oftentimes, we have here's our glazing, we have our mullion here, and then we have our wall. And oftentimes our wall will end before it gets to the window mullion. And this is common in offices, medical offices. We have this condition in our office here. My boss has this. He's got sort of storefront windows, and there's our entry right next to his office, and there's just a gap you can see through. You can just have a normal conversation, through his wall, basically, because there's a gap right here. So we have this cavity path, but then we also have a structure path, because this mullion usually does not have anywhere near the acoustical performance of our wall, especially if this is, high-end condos and we have a really beefy SDC 60 plus wall. A hollow aluminum mullion or something like that is not going to have that same level of acoustic isolation. So we have to address both of those. And that can get really complicated. So here's a solution where we add mass to both sides to improve the acoustical performance of the mullion, but then we also use this to seal up the gap. So we have sealant here, and we minimize the size of this gap. We also have insulation in here, so any sound that gets in here, typically be high frequency, more sound that goes through a small gap, and it'll be attenuated by this insulation, and it also just has a bigger path that it has to travel. And then here we have isolators that are attached to the mullion, and then we have our mullion, these additional housings. This can be some kind of aluminum that matches this, and we have some mass-loaded vinyl in here for additional mass. So the idea is that you're creating something that adds mass to improve the performance of the mullion itself, to improve that structural path. Also, isolation is going to be good. If you just slap some mass onto this, you get less benefit than if you add isolated mass, separated somehow, either with an isolator or it's just not attached directly to the mullion somehow. And then you want to create these seals. So there's other things where you have an acoustical mullion seal. This could just be, foam with some kind of covering on it to make it look decent, and that will seal it, but also add some additional mass and things like that. And here again, you're looking at a test. So these kinds of seals, these seals can also work for expansion joints. Not as much control joints. Expansion joints tend to be bigger. So testing this, you have the wall with the gap sort of built into it, but with drywall cover pieces. This is your base case. And then you take the cover pieces off, you put your seals in, and you test that again. And you see there is still some reduction in this, but you mostly maintain your acoustical performance. And if you just had this gap in here without these seals, this would be an STC, 30 wall or something like that. But again, as you're doing this, you want to make sure that you don't create some sort of structural transmission path here too, right? If you started attaching this drywall over here, you can see here I've got this gap in this drywall, whereas if this were continuous, that creates a structural transmission path through here. So again, for trying to address one of these, we want to make sure we don't create a new issue with our solution to the first one that we had. All right, so a lot of details in there, a lot of things. I do have prior recordings of this available up on our website, so you can go back and look at it. I think I've got a PDF of this too. If anybody's interested, I'm happy to share the PDF so you can kind of go back and look at these. And now we'll see if there are any questions.
Yeah, Mike,
let's see.
Mike, we had a couple questions come through. I don't know. Can you hear me okay?
Yeah, I can hear you. I'll go ahead and go through these. I see these. And
I've answered some of them, so make sure you check the comments.
Okay. Are they in the?
Well,
I'll just read them out too, just in case other people aren't tracking in the thing. So, okay. So Melanie says, if we have a head wall unit in a NICU, how can we accomplish full acoustical value out of a head wall without using 2 layers of gypsum on the inside of the wall and decreasing cost as much as possible? Can I get a link to this presentation for future use on projects? So yeah, I think we'll send out a link after the webinar is done, so you can go when we post the video of this one, you can go see it. And like I said, there's also ones on the PAC website already. If you go to pacinternationalllc.com, there's a webinars. I think it says webinars up at the top. You can go look at that. And if you want a copy of the PDF presentation, Taylor already put her email in the chat, I think, so you can email going to just give it to Taylor. You can email Taylor and she can send it to you, or I can send it to you. But for the head wall are tricky. I guess there's a bunch of different ways. What I've seen a lot of times is that head walls are often added outside of like the primary wall. The head walls are sort of a modular thing that gets added. And if that's the case, then you just make sure that your primary wall meets your acoustical performance goals. And in that, I would say one thing is typically those are steel stud walls. So pay very careful attention to the gauge or mil thickness of those steel studs. Oftentimes the acoustical data that we see for steel stud walls is based off of light gauge, 25 gauge, like 18 mil steel studs. But typically the way those things are built are 20 gauge, 30 mil steel studs, and those perform significantly worse acoustically. So pay attention to that. And if you can, those modular head walls are nice from this sort of detailing standpoint because they put all of those penetrations outside of your acoustical wall, and then you don't have to worry about those as much. And so you probably save a lot of money on dealing with all of these details there. But again, those are complicated. So if you have some specific details or things, feel free to reach out to us and we can talk through those. Could installing constrained layer damped plywood behind cabinets and handrails reduce the need to create gaps in the plywood backing? It's possible, and it depends on the situation. So, I mean, I don't know. I've never seen it tested. So it would be interesting, like proof is in the pudding, right? So it would be interesting to see that tested, to see what it does. My guess is that typically constrained layer damping works really well at like mid and especially like high frequencies. So it's especially good in the speech frequency ranges. So if you're trying to go for speech privacy between offices, patient rooms in the doctor's office or something like that, constrained layer damping can be helpful in those situations, but it typically doesn't do much at low frequencies. And typically when we're trying to meet code minimums for SDC ratings, or we're just designing for housing where, even a little Bluetooth speaker can put out quite a bit of sound energy down at low frequencies, we need that low frequency isolation in order to get a good SDC rating and also to just get good sound isolation. Constrained layer damping typically doesn't do as much at low frequencies, so I don't know that it would be sufficient in that kind of a situation, but I don't know until somebody tests it. What is the detail and hardware that is used to attach blocking for grab bars in acoustic walls? Yes, I see. So if anybody's interested in that, check in the chat. So if this is, this is an AIA presentation, so the point of this is to be informational and not promote specific products. So I was very intentional about not naming any of the products or anything like that. But now that we're past that bit, if you're mounting cabinets to a wall with resilient channel, the PAC RCB, that's the resilient channel backer, is the thing to use. There's a link for that in the Q&A. And if you're mounting cabinets, heavy items, grab bars, whatever, to a wall with sound isolation clips, which would be the RISC 1, the PAC RISC 1, then you would use the RISC 1 backer. And that's the item in there that will help allow you to mount cabinets, heavy items, but maintain your acoustic isolation. And we have tests for all of those. Tests for walls with and without them to show that they sort of maintain the acoustical performance of the wall. Also, it is important to note that both of those, the RISC 1 backer and the RCB, are UL listed, so they are fully approved within UL for use in walls, and they are the only like fully approved acoustically isolated system like within UL that's also got acoustical tests and all that kind of stuff. Usually cabinets are hung with cleats instead of putting up against the wall. Would that help? Are you talking, I don't know, like are you talking about a French cleat or something like that? I mean, anytime, if you have a less rigid connection, sure, that will help acoustically somewhat, but I wouldn't want to rely on that. Certainly I've never seen any test data to sort of substantiate that. There could be a lot of field variation in that. Most of the cabinet installations I see are screwed to the walls. This may also be a West Coast thing in a seismic zone. I'm guessing that you can't just hang a cabinet on a French cleat. My guess is it's got to be screwed to it. But yeah, I don't know. The details always matter. What is the gap between gypsum block and the wall cavity and the back of chipboard in the control joint? Oh, I guess like how big is that? So Mike answered that gap was 1/4 inch filled with fire rated acoustical caulking for an airtight joint. Mike, are you talking about that the gap, the control joint gap itself was a 1/4 inch, or the gap between the drywall on the face of the wall and the drywall that's up against the stud? I thought that was a smaller gap.
The gap between the drywall or the blocking and the gypsum board that was on the Rissa cliffs was 1/4 inch.
That was a 1/4 inch. Okay, and then there was acoustical sealant that smudged into that too when you sealed the control joint. Okay, so a 1/4 inch gap.
Yeah, I think the control joint was a 1/2 inch. You'd have to look on the test reports to verify that. I think it was a 1/2 inch wide control joint.
Yeah. Yeah, folks asking about presentation online, and we'll receive a certificate. Like I said, yeah, if you need a certificate of this, email Taylor. She put her email address in there. And copy head wall. Okay, Everett says, at a window mullion, we sometimes use a mullion mate as connection between an intersecting wall and a window mullion. How does that affect the SDC rating? Mullion mate. You would have to ask the manufacturer of mullion mate how that affects the SDC rating. And again, I would say, like, if you're evaluating any sort of acoustical test data for a product, really A/B comparisons with and without it, or comparing product A against product B, these kinds of things, is really the best way to do it. And those comparisons ideally should be done in the same lab, and ideally back to back or within close timing of each other. There is significant variation between labs. Generally, as an acoustics industry, we have not liked to talk about that, but we are talking about it more and facing it and working on doing a lot to fix it. I'm currently co-chairing a couple interlaboratory studies, both for walls and floor ceiling assemblies, where we're looking into this, and we're working on updates to our standards to reduce variation between labs and things like that. But at this point, if you want a good comparison, really the thing should be tested in the same lab. And so when we've gone and looked at the performance of something like the PAC RCB or the Rizik 1 backer, or a lot of the other things, the shear walls, the other things that we've presented in here, we've done it as a test series where we test all these different options so that we can compare them back to back in the same lab. So if you want to look at the performance of a mullion, it's not enough to just go test the mullion and be like, hey, we got a great result for this, right? You should test it without it. And I'm pretty sure, it's been a little while since I've looked at it, but like the mullion test that we have, that this data, can I go over here and go back? This thing that we tested, pretty sure we have a test for this mullion kind of wall configuration. We did the wall, just the bare wall. You see here, the wall itself was an STC 64. And when we put the mullion in here with this solution, it was an STC 58. So it did reduce the STC rating because we still have all these gaps in this thing. But like we have that comparison. Because if we just published the STC 58 and we're like, hey, our mullion solution is an STC 58, be like, that's great, awesome. But that doesn't really give you any context for it. So you got to make sure that you have that context when you're evaluating an acoustical product. Don't forget, wait, there's more of these. Certificate of completion. Okay, Robin says, I once saw a renovation article where they used a full wall membrane behind the sheetrock that was some sort of rubber-like material. Have you ever seen this? I've seen a lot of random stuff. A lot of it doesn't work. Single-family home renovation stuff, there's a lot of random stuff out on the internet that I would not do, especially if it's a fire-rated wall. Probably putting rubber in it, not ideal. It may have been mass-loaded vinyl. That's a fairly common thing that you'll see suggested on the internet. Mass-loaded vinyl adds mass. It's in the name. It doesn't really add any more mass than drywall. And I would say the vast majority of situations for architectural building acoustics, noise control, mass-loaded vinyl doesn't make sense. Just add another layer of drywall. There are other situations like industrial noise control, those kinds of things, where mass-loaded vinyl is 100% the thing. Recommended a ton for those kinds of situations. But also like those kinds of things are not going to give you this acoustic isolation because you're just going to screw right through them and into the studs to mount your cabinet. And those screws are going to be a rigid path that's going to transmit sound. So you're not really getting any benefit there. Chips Davis. Hey, Chips, I hope you're doing well. Chips says, don't forget covering the couplings of the electrical boxes. I don't know if Chips means like just if they're touching back to back, or between the electrical box and the drywall. But either way, don't do either of those. You want to make sure that they're separate. They don't touch each other. If you have a thin wall and you have back-to-back electrical boxes, they could touch each other. And if you've got acoustic isolation in that wall, you've now short-circuited it because, again, you've created this rigid path. So again, you just want to, get out your pencil and trace it. Do I have a rigid path all the way through? If so, that's an issue, and you need to figure out how to disconnect it. Considerations for exterior wall using SIP. Yeah, so SIP is structural insulated panel, so it's like this is OSB with EPS foam insulation in between, so it's a sandwich panel. So it's this is one of those things where I said sometimes what's good for thermal decoupling and isolation is also good for acoustics. SIPs are one where what's good for thermal is not good for acoustics. It's a fairly lightweight and rigid panel, which is great for transmitting sound. We use lightweight, rigid things usually to produce sound, like speaker cones and instruments and things like that. So it depends on what you're trying to do with the SIP, but generally I would say the shear wall thing that I showed in here, right? The shear wall is a rigid panel with OSB probably on either side. And so we have to add the acoustic isolation. So that's where we'd use Rizik ones and clips with insulation, fiberglass insulation in that air cavity, and then a layer of drywall. So that's probably what I would do if I were using SIPs. I would do that. That should get you pretty decent performance out of it. And actually, Mike, do we have test data on SIPs? I feel like somebody tested SIPs with our Rizik one, but maybe we don't actually have the test data for it. Is that right?
Yeah, we do have the test on the database. I don't know if they're public, Mike.
I can't remember, but now that we mentioned the database, so here's our website, and we have these. This is an old version of this, but we have our assembly selectors. So we've got a lot of people that have already registered for this and use this on a regular basis, but we have these assembly selectors where you can go. It requires you to register, and right now our login and user registration is very slow to load, so just practice your patience. It does eventually load and you can log in or register. But if you go to this, as you can see in the animation here, we've got a database, one for floor ceiling assemblies and one for walls, where you can go sort through, filter by assembly type. So if we have them publicly available, which I think we actually do, because I feel like I keep seeing them whenever I log into it.
Yeah.
There's a thing for assembly type. You can look at that. SIP might be one of the assembly types, and you can go look at those. And I think we've got some test data for it. There's also a whole bunch of other test data in there for those kinds of things. The details shown in the presentation, is there a library of these recommended details that we can reference on our project? Excuse me. Not yet is the short answer. If you go on our website and you look on our different product pages, like the RCB or the Rizik One Backer, I don't know why my presentation is like automatically going. I'll stop sharing. If you go look on our website, we have some of these details shown in various forms for different specific products. I have had for quite some time now a plan. We've just been too busy doing spring shop drawings and a bunch of other things, but have had a plan to create a database of these details. So right now, if you want to see these details, we can give you a PDF copy of this presentation. You can also go watch one of the recorded videos previously, or this one when it comes out. But do stay tuned and keep asking about a database of these details, because it is a thing that we intend to put together. Part of it is, if we're going to do it, we want to do it well, and there'll be CAD details. They'll look better than my sketches that I have in here. We'll have CAD details for some of these. We might have 3D Revit details. We're also working on eventually releasing, hopefully, BIM objects for a lot of our products so that your architects can use those and incorporate those into your drawings. So we understand that there's a need and a desire for that, and we're working on it. So stay tuned. Anything else? Anything that popped up in the chat, Mike? Or I see that there are some things over here too.
Yeah, there are some questions in the chat.
On the door head and jamb detail, would it make sense to case the entire opening rather than have the narrow piece of drywall? I'm not sure how that narrow strip of drywall would be fastened. So for a lot of these, there's a lot of different ways to do these. And what makes sense for one project may not make sense for another project, because for these door and window sills and jambs and headers and things like that, your width could vary significantly, and that could affect whether or not you can kind of cantilever out this little piece of drywall or not. So, which is why at the beginning I talked about sort of this whole framework of how to think about these things in terms of tracing your structural and your cavity paths and paying attention to those. So I would really take what I have in here as a detail as a suggestion and a way to think about this and sort of an approach, and then take your specific situation and see if you can blend the two. And if you want help, reach out to us. We're happy to have a meeting with you to kind of talk through those things, talk about these specific applications, how you can best implement PAC's products in there. And that's really where PAC has a lot of expertise and can be really helpful, is not just understanding the acoustics, but also understanding the construction and how these things are actually built. This is PAC's 50th anniversary, and not PAC necessarily as a noise control company, but PAC as involved in the construction industry. So PAC's founder Elzo started 50 years ago as a lather, I think, doing lath and plaster. He ran his own drywall contracting business. He ran a drywall distribution yard. He ran an export business where he and his son Mike supplied all of the materials to build military bases overseas and things. So they have this huge wealth of knowledge in the construction industry. So if you want to dig into the deep details of how to build something, and you want to know how it was built 30 years ago versus how it's built now, Mike and Elzo can tell you. So feel free to reach out to us and tap into that resource. Anything else? The details that I'm seeing in here, I'm missing, Mike?
I think you got it covered pretty well. Sorry, I'm walking through the trade show.
Oh yeah. So if anybody didn't see it at the beginning, Mike Gernhardt, our CEO, and Dave Dambois, our new sales director, are both at AWCI. They're at you put it in the beginning, they're booth something or other, booth number 359. So if you happen to be at AWCI or headed to AWCI, or folks that are there, tell them to stop by the PAC booth. Say hi. You can see a lot of the products probably that I mentioned in here. You can ask them your construction questions, and also you can see our new product, the Rizik Adapt, which is an alternative to spring isolators that provides similar performance, acoustical performance, but is way easier and simpler and faster to install. So if you're there, check that out. And with that, I think I will call it a day. Thanks you everybody so much for joining, and thanks to all the folks that we still got quite a few folks online, so thank you all. And yeah, if anybody else has a question, I'll stay on for a few more minutes. You can pop it in the Q&A. Salem says, seriously, come on, you need to get on the details. All right, we'll work on it. I appreciate that you want them. All right, thanks everybody. I hope everybody has a great day, and we'll do another one of these. Part 2 ceilings is next month. Stay tuned for that, and we've got a couple more coming up after that too. All right.